Well, very happy to have Christina Gao back again to tell us about neutrino mass bounds. Take it away.
Yeah, thanks for letting me visit again. So, when I moved to China, I felt it's because when I was back here, I was working on some axion quantum sensing, whatever, and then these sensing stuff got super sensitive somehow. So I thought, okay, maybe I should work on something else so that I'll not get
sensitive in the sense of national security,
exactly.
Not in the sense of physics.
Not in the sense of in the sense of national security, because these are controlled by people who are not physicists, and then they decide they're sensitive, right? So, so then I was like, okay, we should work on something not to do with national security. What's that? Something about neutrinos.
But that's also controlled by non-physicists.
That's true. Well, to be specific, it's the oscillation experiments. If you move away from oscillation experiments, it's less controlled by people who are non-physicists. So anyway, I was very happy to got to know some of my collaborators, and then we talked, and then we're like, okay, why don't we try this out? So this is about having using a specific model in cosmology, explore its cosmological consequences, and try to reconcile neutrino mass bonds from laboratory-based experiments like oscillations with cosmological indirect constraints, okay, mostly. So this paper should be out soon, as you see, the authors are already there, their institutes are there. Okay, so I've moved to Shenzhen in China, which is actually very close to Hong Kong. So if you ever have a chance to visit Hong Kong, because you don't need a visa to visit Hong Kong, I think you can just go. And then you can cross the border very easily and then stay in Shenzhen for a couple of days without a visa too, I think, nowadays.
How come Macau's on the map but not Hong Kong?
I have no idea. We can,
Macau is on the map but no Hong Kong.
It's like a Google thing. We can go back to the full website to check.
Well, Taiwan's there, so
Yeah,
it's fine.
but so this part of China. My school, yeah. This is a very sort of a newish school, so the University of Science and Technology in Shenzhen. It's a good school because it allows me to travel freely, and I don't have to come up with too many excuses to move away from teaching. I still have teaching duty this quarter, but they are pretty relaxed as you're rearranging or trying to get someone covered. So it's a good school, pretty relaxed. Unlike other schools in mainland China. So neutrinos, we know neutrinos have 3 flavors. And then we have measured many properties of neutrinos. For example, through oscillation experiments, we know that neutrinos have masses, and at least 2 of them are massive. So this is just showing 2 possible ordering of the neutrino masses. Depending on which ordering you pick, the total neutrino mass is different. Okay. So this is some bounds from oscillation experiments. Also, directly we can measure neutrino mass, especially this state, the electron neutrino, anti-electron neutrino from the tritium decay. One can look at the end point of this 3-body decay and then try to infer what's the neutrino mass here. So this is the latest bound from Cochrane experiment, and the place is bound as 0.45 eV. So it's getting better.
So they used to have this data that showed it went out past the end. So they said the mass squared was negative.
Okay.
They fixed that?
I don't know about that. Maybe you can tell me later. I don't know which, is there a paper?
There are many papers by Ellen Kostelecki.
I don't know. You can tell me later about this. Okay. So this is the terrestrial neutrino experiment. Other things we know about neutrinos is that they can interact by exchanging Z bosons through this bystander model. Below the Z mass, the effective for Fermion interaction is given by this coupling constant, roughly speaking. Okay, so these are something about like what we know from terrestrial experiments. On the other side, actually, neutrinos can impact cosmology because they behave not like cold dark matter. They're not completely like radiation. They're sort of transition while the universe expands. So they're very special, even though they are only like a very small component of the whole universe. So this is like a history that is related to neutrino. So around here, I says, before BBN, neutrino decouples from the standard model bath of electron photons. Soon, then there is the Big Bang nuclear synthesis. And then after neutrino decouples, they are sort of free streaming. They're still relativistic, but they are not interacting much with the rest of the standard model particles. And later on, there is the matter radiation quality, and very soon after that, it's the recombination. And then after recombination, you get the cosmic microwave photons. Okay, so these are the relevant these events lead to observables that will be useful for us to study neutrino properties. So here it says, around here to somewhere where neutrino become non-relativistic. Well, of course, it depends on what's the actual mass of the neutrinos. Neutrinos are free streaming, and then after they become non-relativistic, they're just like cold dark matter. So there are many studies of how neutrinos could impact cosmology. One of the most well-known results is that neutrino mass can impact growth of structure, as shown in this figure. So this is like something I'm still learning, this part of the neutrino properties. This is showing the linear matter power spectrum, and then K is the wave number. So large K is to do with early times, so small k is late times. So early times, and then this, so these different curves are assuming different neutrino mass, and this, because we have 3 neutrinos here, they're assuming 2 massless, 1 massive, so they're just assuming. So this, as we can, it's showing that they're only sensitive to the total neutrino mass. They don't actually care what's the ordering, as long as because because the curves that differ very much is before neutrinos become non-relativistic. Okay, and then the reason. So this is what I understood. So 0.05 eV. So when neutrino is less massive, they don't impede growth of structure. Okay, so when they become more and more massive, they actually start to impede the growth of structure more. And the reason
why is large K growth of structure?
Large K is small scale, so small scale, the structure grows from small scale, and then on the gravity, the large scale starts to grow. So you always grow from the small scale. And then here, and the reason when you have like more massive neutrinos, the structure is less grown, is because here, all the neutrinos are still like relativistic. Okay, so they're not clustered. So if you assume the total mass is like fixed, the more mass is in neutrino, the less mass is in cold dark matter. So this is what I understood why when you have more neutrino mass, the structure is impeded more. The growth of structure is impeded more. Yeah. So, but then after they become non-relativistic, it doesn't really matter. They just behave part of the cold dark matter.
So if you wanted to get around this if I wanted to live with a more massive neutrino, I could imagine trying to have, I think the neutrino decoupling temperature is around a GeV, is that right, if I remember?
No, neutrino decoupling is around right before BBN.
It's right before BBN.
Yeah.
It's right around 10 MeV or something.
Yeah.
Okay, so then it's hard to change, because it's hard to change the initial abundance of neutrinos then without messing up BBN, unless you do something right at the very beginning of BBN.
Exactly. Yeah, that's the
Okay.
trick of this whole. There is like a small community working on this sort of thing,
Yeah.
and that's to mess stuff after BBN, so
Yeah.
you don't get
Yeah, yeah, yeah.
messed up by so you don't get excluded by BBN.
Because otherwise you could imagine, yeah, so otherwise you could imagine changing the neutrino abundance, right, and then playing with that, and I guess,
Just temporarily change the neutron decay final state.
sure, I don't know. Okay, anyway,
Yeah.
I want to hear the rest of your story.
Yeah, yeah. So the yeah, exactly. The story is about messing things after BBN. Okay, so yeah, so because of this property of neutrino, you can actually constrain some properties of them through precision cosmology. For example, you can constrain the total neutrino mass. And this is also the latest Planck plus Desi analysis, assuming lambda CDM, so nothing new, no new physics, just the standard model. It's in the
Is
cosmology.
it the sum of masses or the sum of absolute value of masses?
The sum of the masses, so there's no negative masses, I believe. So it's the sum.
You could have a relative phase.
Well, they're actually not sensitive to the ordering, so they actually don't really care. All they care is like what's the energy density is in neutrino for them. So actually the trend is there is a trend that seems to show they don't really want any neutrino. So that means there's more like clustering of structure than what they would expect it from just from some oscillation experiments. Okay. So this is one thing. So this indirect constraints, right? Indirect bound on neutrino masses, 10 orders magnitude almost. Almost better than this catch ring, which is a direct constraint on neutrino mass. However, from neutrino oscillation, we know that depending on the ordering, the total neutrino mass has to be bigger than 0.06 if it's normal ordering. If it's inverted ordering, it's 0.1. So if you look at here, the lambda CDM cosmology already ruled out inverted hierarchy.
Do they claim that, or?
I think so, yeah. If the lambda CDM cosmology, they ruled out inverted hierarchy.
So we don't need to build in.
Huh?
We don't need to build in.
Well, that's the thing. Well, because this is an indirect constraint, right? If you can mess up the cosmology, you can relax the bound. And that's the point. That's why we can still play, because it's indirect. Right? Okay. So one message is, cosmological measurements of the total neutrino mass are seemingly at odds with terrestrial experiments. Next thing is, because we have lots of observables related to this period, right, of the early universe, the precision cosmology can also be sensitive to free streaming properties of the neutrinos. Meaning, if neutrino is only interacting via Z below BBN, they're not really interacting much with anything. Okay, they're just freely, they're not interacting. They're relativistic. Well, however, if neutrino can interact via a light scalar, so that the self-interaction among neutrinos are stronger, the neutrinos are no longer freely streaming particles. They're more like a fluid, all coupled together. So in that sense, actually, you can imagine if they're no longer free streaming, they're more clustered together. They actually help structure growing better. So that's something.
Wouldn't the scalar interaction be repulsive?
I think it's attractive. The scalar interaction is always attractive, right? You can have vector interaction that's repulsive. The scalar is always attractive.
Yes.
I think.
Thank you.
Yeah, I think. Okay, so because we have all these probes, we are actually sensitive to whether neutrino are free streaming, and if they're if they have secret interactions, it helps with other cosmological tensions, for example, H-naught tensions or stuff. But I'm not going to talk about them because I'm not super familiar with those topics. But self-interaction or secret interactions in neutrinos are sort of interest for people who study cosmology.
How would you get this interaction for neutrinos and not electrons?
That's a great point. It's really hard. It's very constrained if you try to build things that obey gauge invariance and all these things, right? So it's not easy. But we can. That's why there's like.
You could have just direct neutrinos and have right-handed neutrino interactions. If you just have direct neutrinos.
Mm-hmm. Yeah, there is
then
a
you're
paper about that.
just acting on
The right-handed, yes, there was a paper on this sort of thing. I think it's all similar to that kind of story. This game, it's very similar. It's trying to couple its left-hand neutrinos additional light species, and then you try to introduce self-interaction among these other light species. So that's just the game. Yeah. So yeah. So here, for example. These are my two collaborators. Of course, they are super into neutrino self-interaction. And they did some MCMC fitting with Planck plus ACT data or just ACT data. These are CMB maps. Okay. Here, what they're doing is different. Is that they assume. So normally you would assume you would introduce a self-interaction among all species of neutrinos. So they're like, okay, let's not worry about how to construct the model, but imagine the self-interaction is only it is mediated by one flavor or two flavor. Okay, so here they're assuming, let's say one flavor is free streaming, two is coupled, or two flavors is free streaming, one is coupled. So not worry about what actual model would give you that, just do the cosmology and see what happens. And what they find is that this is the one, 1D posterior, or a likelihood, the higher it is, the more favored it is. If you allow self-interaction to be only among a subfraction of neutrinos, it is actually as preferred as lambda CDM. Okay, so that's interesting. Then you're like, oh well, how do you actually get those type of behaviors, right? So that's something.
On the left, there's this big bump for Planck plus ACT, but it's
just
no bump
ACT
on
alone?
ACT alone.
Yeah.
ACT alone rules it out, and then
No, ACT
Planck.
alone prefers this strongly interacting mode. Here,
But adding data completely changes it.
adding Planck adding Planck will not. So do not favor strongly interacting as much if all three flavors of neutrinos are coupled.
So Planck
What's
alone would
the-
just have a bump at -4.
Planck alone is like lambda CDM. Planck alone, lambda CDM is more favored compared to universally coupled self-interaction.
Wait, is that
What is the vertical axis?
It's some 1D posterior. I don't know why they never give this. They just tell me it's 1D posterior. So the higher it is, the more favored it is.
But
right?
what about no? Sorry, all three are free streaming. What would be the
Free stream.
corresponding? Basically, no strong interaction. There's
Free
three.
That would be lambda CDM, right?
Yes.
Yeah. So
Is that on the top? No, I don't.
It
Yeah,
would be
this
a
is not-
horizontal line, right?
Yeah,
I mean,
this
it
is
would be
not on the
independent of
feed.
G effective.
yeah, this is not on this thing.
And how high does it go?
yeah?
I think it goes, according to them, it goes as much as this peak. Yeah, should
But
be similar.
Isn't there more probability on the left than on the right?
Hmm?
There's a
This-
big broad peak that's just as high.
Yeah, so this big broad peak is higher than this red peak here. So if you have universally coupled self-interacting neutrinos, then the strongly interacting mode is not as favored. However, if you allow yourself to entertain the possibility if only a subfraction of them are self-interacting,
Okay.
not all of them, then this becomes alive again, right?
It's
So-
alive, but I'm just saying there's a much bigger parameter space on the left.
Well,
No, this is a PDF, right? So it's depending on what's the self-interacting strength.
Right, but there's a whole range of interaction strengths that are highly likely.
Yeah, yeah. So yeah.
If I take this to 0, shouldn't it be like all three are free streaming, and then it goes down?
Yeah, because, well, this,
It doesn't prefer the free streaming one.
no, this one is 3C, so it's all three coupled.
Yeah, but the coupling very small. When you take the coupling to 0.
You're saying if you go all the way to the left,
That's to the right, though, right? Because G effective is,
Small this
Small,
way,
okay.
small this way, small this way.
Right.
yes. So if you go to the left, I guess he's asking if
Does it
you
go up
go
again?
to the lambda CDM line, if you just keep following any one of those lines to the left, wouldn't you expect to just get
Lambda CDM.
lambda
yeah.
CDM? I think that's the
so.
question.
I think so, yeah. I've seen another plot with not this line, like this. But if you go to the left, you go back to lambda CDM.
but is it higher or lower than these peaks?
As much as high as these, we can look it up.
So they go
later.
up, it goes
I
up
think
as you
it
go
should
left.
be. I assume they should be. I don't. Yeah, these. I don't know why they stop it here. Yeah.
Then isn't there something weird about this left peak? Then the left peak is as good as the right one, right? At least for the three
Yeah.
self-interaction with
Yeah.
quite
Yeah.
small coupling.
Yeah, yeah, but this is not.
It's non-zero. then
Yeah,
it
it's
fits,
non-zero. So this mode is actually called. They call it like moderately interacting. So this is not like no interaction. No interaction is way smaller on the scale, right?
So this would be suppressed by 10 eV.
10 eV over.
G effective is 1 over 10 eV squared.
Yeah. 1 over 10 eV. G effective here
No,
on the 10
it's
to minus
weaker,
10,
right?
and this is 10
Sorry.
MeV.
So it's 1 over 100 MeV.
Yeah, this is
Squared.
100. Yeah, 100 MeV. This is 10 MeV. So still much.
So 100 MeV is the sweet spot. That's what you're telling us from this plot.
No. Yes. If you allow. Yes, it's a sweet spot if all of them are coupled. Okay. However, if you allow yourself to entertain that only a subfraction of the coupled, this becomes favored again. That's the message. And then both of these modes are stronger than the boson-mediated interaction. Okay, so this is the strongly interacting mode. This is the moderately interacting mode.
And this act alone doesn't favor the left peak at all. And the plus Planck you favor it. Doesn't matter, just Planck alone just like that, the left peak very much.
Yeah, yeah, yes. But both of them are not standard model neutrino interactions. Because you're sitting here, this is 1 over 100 MeV squared. This is 1 over 10 MeV squared.
So what is ACT?
ACT is a ground-based telescope looking at, I don't remember the whole name, but it's a CMB. It's looking at
Doing some
CMB.
support, right?
Yeah, it's a ground-based telescope looking at CMB.
Polarization.
Is it? Let's look.
And are they really looking at, my question is, are they really measuring different observables? So is this a statement that different observables prefer different things, or it's a statement that two experiments are disagreeing with each other?
I think it's just two experiments have a different systematics. Like
They're in principle measuring the same thing?
Yes.
Okay.
Yeah, for these software stuff, they just measure a small portion of
The sky,
Yeah,
do something
okay, I see.
better.
So, yeah, but they're in principle trying to get the same
Same thing,
observables. It's
yeah.
not that they're looking at different
No.
parts of the spectrum or something like that,
No,
right?
no. I think they're both trying
Okay.
to look at CMB.
Okay. All right.
That's my feeling
In the
of
past, when I've seen
cosmological
talks
stuff.
where you have two cosmology experiments disagreeing with each other, the people on both experiments don't care to, they not that they don't care, but they don't try to explain why. They just
Yeah.
how
Usually
it
it's far. So some other people told me combining data sets from different experiments is very dirty. So
yeah. Anyway, it's okay. Yeah,
Yeah,
there's
it's
probably
just-
all sorts of priors. And
yeah,
stuff
exactly.
Like that that
It's
come
just very very.
in. Yeah.
And there's this. Of course, this gives you endless playgrounds to do things, but on the
Yeah.
other hand, it's just very dirty. It's like a very dirty game. And
Also, here is this other labels massless means in those columns it's not completely massless.
no, they're mass. So yeah, so this because they're looking at the growth structure at the high K. So for those Ks, the neutrino mass don't really matter because there the neutrinos are just like massless particles. So looking at so this they're not sensitive to the total neutrino mass for this part. Yeah. Okay. So there is and why are people interested in self-interaction of neutrinos is because there are some other studies show that self-interaction of neutrino can help alleviate H0 tension or these things. Not completely solving it, but like relax these things. So this is sort of interesting. Yeah, let's see. Okay, so back to the actual model itself. So if you're serious about constructing interactions among neutrinos via introducing light scalar, it's actually very, very difficult because standard model neutrino is part of SU2 left-handed doublet. Once you introduce the 5, so M5 is the mass of the mediator scalar, the scalar mediator, and G5 is just the coupling between neutrinos and phi. So here, this study actually studies. So again, they don't even write a model. They just say, well, let's assume there is an interaction mediated by phi among different neutrinos, and they're allowed to have different couplings among different flavors. And even that is already very, very well constrained. For example, here, so this on all of them, they actually show 2 bands. This SI nu is the strongly interacting mode of the peak you saw on the further, the first peak. The moderately interacting neutrino is this broader peak. So if you hear, so this is the MI peak, this is the SI peak. Okay, so here they show, well, in order to get SI peak or MI peak, this is the amount of interaction and the mediator mass you need. Well, but look, they're almost all ruled out by taking into account of terrestrial experiments.
Except for Dirac nu tau.
Except nu tau.
Bottom
yeah.
right.
Yeah.
Dirac
this
nu
part.
tau nicely follows that medium line.
Oh yeah, Dirac nu. Yes, there's a Dirac nu. There's a yeah.
Awesome.
And is there any let constraint just from Z to nu phi? I see you have tau to
Yeah, I mean the
nu
invisible width.
phi, but maybe that's because
It's-
these are pretty small couplings, right?
Mhm.
But I would have thought near the top of the plot you might have some
Yes,
left
there
bounds.
is. Yes, there is actually. It
Yeah.
was showing some other plot. I chose this plot. Yeah, it was pretty up here.
Yeah.
It's all the way to the right.
Yeah, so that
Yeah,
might only
it will be all the way to the right, and it's this up here. But for me, because I'm actually going to talk about mediator mass below MeV, so I'm sort of more interested in this part of parameter space.
Okay.
And this plot nicely show that naively, just having a scalar coupled to neutrino is very difficult to reproduce the amount of self-interaction you need. So this is the introduction. Well, the second part of the introduction is trying to say self-interacting neutrinos are entertaining possibilities from cosmology, but they're severely constrained by astrophysics and laboratory experiments. And and there is a question mark of how you actually can get flavor-specific SI neutrinos. Well, that's from a model building point of view, it's just kind of impossible for me because I am not that smart. I don't know how to do just tau only things. But as we will show, one can mimic this behavior by having like light species coupled to neutrinos. Okay, so this is the outline, introductions there, and the rest of the story is I'll tell you that if we allow neutrinos to couple to some dark radiation, this can...
Maybe introducing the self-interacting help to solve the daisy conflict with the... No?
No, it's more like to do with... No, it's, the lambda CDM is as preferred. This is the self-interaction, let's say, is allowed by cosmology, and it helps. There is a time that H0 tension was like people are very interested, and self-interacting neutrino.
Yeah, I know that part. So it doesn't help to address the AC measurement.
I don't. No. It's nothing to do with neutrino mass story. It's like a separate story. I think. Yeah.
But the fact that the upper bound and the lower bounds for the normal hierarchy are the same, almost the same, does it open up a window there?
Okay, that's what you want to talk about next.
Exactly.
Okay, you are not talking about that particular one. You want to talk about the dark radiation. Okay.
Yes.
Now I see it.
Yeah, I want to play with a model that allows you to have extra stuff so that you open up the mass bound at the same time mimicking the self-interacting properties of neutrinos and not ruled out by any laboratory experiment. So that's the game. Okay, so that's the game.
Right.
Yeah, so basically what you want to do is, in order to not mess up Big Bang nuclear synthesis, you only want to modify cosmology after Big Bang nuclear synthesis. Okay, that's for me, but some other people will tell me you can modify several different things at the same time to evade the BBN bounds. I'm not like my level of skill set is not there yet. So I try to stay safe, be like, okay, let's just mess things up after BBN. And it was like done before, okay? So it was played by people, for example, Nikita, Nasher, they wrote 2 papers on how do you get sub-GeV thermal dark matter by having like a dark sector interacting with neutrinos after BBN. And also there are some other papers, this is more recent, and this is also by playing this game, and then they claim you can relax cosmological bond on the total neutrino mass. Let's see. So this is so the story is roughly like this. Okay, so you begin with 2 different sectors. This is the standard model sector with neutrinos and the rest of the photons. The neutrino decouples after the neutrino decoupling with their temperature T nu, and there's a different dark sector, let's call it TDR. Okay, so there are at different temperatures there are very, very suppressed interactions between them, and later time, okay, so some phi force mediated by phi becomes very active, and you can probably guess this is like a resonance effect, right? Because you only want it to open for like one window, but not all the time. And this brings the temperature, it is trying to thermalize 2 sectors. So this will make the neutrino cool and transferring part of its kinetic energy into the dark radiation, raising the temperature until they're approximately equal, like they become equilibrated. Okay, later on, this interaction is no longer as effective, and the chi just kinetically decouple. So this is like neutrino decouple from standard model. They still maintain the same temperature, but they're just like free streaming on their own, like this. So here, one can imagine you can engineer some coupling so that the chi's are self-interacting, but the standard model neutrinos, standard model-like neutrinos are not self-interacting. Okay, so this is the total story. And because you, so let's say, so because you're not like messing any things before BBN or like close to BBN, the total and effective from like BBN constraints are 3.04, like, or whatever it has to be. It's not like messed up, and it's provided just from neutrinos. And then after you equilibrated two sectors and transferring part of the neutrino energy into the dark sector, the total and effective is still the same. Okay, it's not changed too much. Well, depending on whether phi is part of the bath or not. Because if there is like some story, there is a slight increase of total and effective phi is part of the bath in any of this history. But let's say phi is like very, very short-lived because it decay immediately to chi. So let's say this is it has almost a negligible abundance. The total and effective is not drastically changed, but now the amount of energy carried by neutrino is split between the nu and the chi. Okay, so that's what you get after doing all of these things. That's like the features of what you want to achieve, what you want. And so the model here we're doing is just a type 1 seesaw kind of model. Okay, see here is your standard model parts of the left-handed doublet, and Higgs is right-handed neutrinos, which acts as mediators between the standard model and this dark sector. Dark sector, minimally, we just assume it has a scalar phi and some radiation chi. So chi could be one species or two species or whatever.
So I don't think I understood why, if you go back, why does you're sort of, it's like, if I just very crudely think of this as you're sort of replacing the neutrinos with this self-interacting radiation.
Sure.
Why does that loosen the constraints? Is it because you can play with the masses of the sort of the chi's or the things that are kind of replacing the neutrinos, and of course there aren't any lab constraints on their masses. And so is that the basic idea? Now you can play with that, and they are sort of playing the role of the neutrinos, but now you have a lot more freedom. That's the basic idea?
Yes, that's it. Yeah, because
Okay.
cosmology cannot distinguish between chi and neutrinos.
Yeah.
They have the same abundance.
Right, they're just some decoupled species
Exactly,
with some temperature.
exactly. Having the
Okay,
same
so that's-
temperature, they're just different
Right.
decoupled species. Yeah, exactly. That's it. That's the essence of this thing. And the rest is just try to, examine this model actually exists, and just demonstrate this is a possible solution, right? So that's like the rest of the thing. You just say, okay, this can exist from.
Isn't the lifetime of the universe at VBN like famously like a minute or something like that?
Yeah, some
Isn't it
people.
something- I'm just a second. So I'm wondering, a second, maybe you can't do it. I was wondering, you couldn't do this with neutrino decays? Have some very long-lived neutrinos so we don't ever see
3
them.
minutes.
That's why the
3
book
minutes.
is
Yeah,
called
the first 3 minutes. That's what I'm
First
saying.
3 minutes. Yeah.
That's what I'm saying. That's why famously. So I'm just asking. Yeah, 3 minutes. Yeah, exactly. So I'm just wondering. I mean, and people thought about neutrino decays.
Yeah.
Because maybe they're very long-lived, so they're decaying after nucleosynthesis. Then they have to decay to something lighter, and maybe that's the wrong direction. You want these things heavier to have. No,
Yeah, that's a neutrino decay is definitely a solution to relax neutrino mass balance. I've seen papers, but I never read them. But I've seen papers. I think Yushin worked on some of these neutrino decay things.
Because I mean, naively, the cosmology would, the cosmological constraint is saying neutrinos have to be lighter than something. So you could, if these guys or chi's are playing the role of the neutrinos, they can be as light as you want. Very naively.
Yeah.
And then you just need to make the lifetime long enough that you don't mess with laboratory experiments, so
Yeah.
that neutrinos don't decay on the way from you know, you're one place to another and you're long, I guess from the sun is probably the one you're most worried about.
8 minutes.
8 minutes, well, I mean, you wanted longer, much longer than 3 minutes, right? You wanted to decay somewhere between BBN and maturation inequality. Yeah, that's true. So how many light years is that? Anyway, okay, I don't want to derail you, but anyway,
Yeah.
okay. Just,
No,
I haven't
no.
thought about this stuff either,
Yeah.
so I'm just
yeah,
asking.
but there's I think for me, the reason I'm sort of interested in playing this is because I think there is some room to, you know, use the knowledge of some models or like what we know about SU2 left-handed doublet.
Yeah.
And then the cosmologists, of course, they don't really care about these things, but then they just want you to tell them this can work. So, which is like you know, I don't really know much cosmology. I'm learning a lot through this, but I can, you know, I see I can do this, right? So I tell them, oh, we can do this. This is doable. So so basically this is the model. You assume some mass hierarchy, right? Because you need to make sure things happen at the right time for this cosmology. There are lots of issues with fine-tuning or whatever. We're not going to worry about these, okay? Crucially, some features right here. So because we're doing type 1 seesaw, so the couplings is to do with mass generation of neutrinos. And specifically this coupling, right, that the phi that mediates among neutrinos is going to be, this self-interaction is very, very suppressed. Actually, this coupling is suppressed by the neutrino mass divided by the heavy right-handed neutrino mass. So this makes you free from all the bounds, essentially, that's it. And the next thing is, well, as we said, the chi, because here, this coupling has no constraint. You can just do whatever you want as long as you, do whatever you want, I think. So this can mimic strongly interacting neutrinos in cosmology. Okay, so you want to compute some rate, right? So these are different processes that will be important in this evolution. First of all, it's just the self-interaction among neutrinos. Now there are two modes, right? The Z mode and the phi mode. But as we said, because this coupling is suppressed by the light neutrino mass divided by the heavy right-handed neutrino mass. So this is actually nothing compared to the Z. So the Z boson mediated interaction is much higher than this. So this gives you the green solid line. It's just the neutrino for fermion interaction. It drops as the temperature goes down. So this is the photon temperature from 10 MeV is the dBn, okay, where the dBn is, until 10 to the minus 5 MeV, so 10 eV. So the CMB or whatever is way to the right. So CMB whatever is like 0.3 eV, I think, or 3 eV, 0.3 eV. 0.5, I forgot. Roughly, let's say 1 eV. Okay, so it's to the right. Okay, not there. Next thing, well, you want to transfer neutrino energy to the dark sector chi through this resonance effect. And this is just directly controlled by where you place the phi mass. So here, this is given by this solid black line. Here we assume the phi mass is like at 10 to the minus 2 eV. So if you compute this shows the resonance behavior around here, and then after that it just like drops, goes down like for fermion interaction. Look the scaling here and the green lines, because they're all for fermion interaction controlled by the temperature. They just scale the same way as you cool down. And again, the self-interaction of chi's, well, this is not suppressed at all because it's just some new coupling which is not ruled out by anything, right? So you can make it as large as you want. So here, this is shown by the red dashed line, and it goes like exactly the same way as this process, but like 10 times bigger, because this side is suppressed, this side is not suppressed. That's it. Lastly, there is this dotted line, this is a more complicated process, is that in this model, you actually always have this kind of T-channel production phi. It's always there, and you have to be careful. You don't want to produce phi prematurely, because producing them at too early will mess up your BBN and effective bounds. But this can always be suppressed by choosing, writing the neutrino that is large enough. Okay, so basically you have these 4 processes that are important in this cosmology.
So the claim is even one massless scalar is too much at in equilibrium is too much at BBN. That's what the bounds say now.
What?
Because you're saying phi cannot be in equilibrium during BBN. That's just an ineffective bound.
Yeah, the ineffective.
One is already too much.
Too much, yeah. Because ineffective at BBN is 3.3 or 3.4 or something, so
Okay.
it's already too much.
Okay.
Yeah.
So the blue dot, for the blue dot curve, you assume the writing neutrino mass. What's the writing
Mass
neutrino
10 MeV.
You assume that's assume 10 MeV.
That's assumed 10. Yeah, later on we'll do a scan to just check which part of the parameter space allows you to effectively cool the neutrinos to chi. Yeah. So this is like a benchmark just to check the temperature of different sectors, assuming thermal distribution. So here, we're showing 3 different lines. One is the electron neutrino temperature. This is the muon neutrino, and then we assume muon neutrino as the same as the tau neutrino temperature, and then this is the dark radiation temperature. So here, the phi mass is chosen as 0.01 MeV, so like roughly here. And then their initial temperature is set to be, the neutrino is like the same before, before BBN, right? So after neutrino decoupling, they just like drop. After like the electron-positron annihilation or something, right? So like here, they should be around this line, this famous like 0.7 something line. If not given, if you don't have extra radiation, but here it goes below the usual 0.7 temperature because part of their energy becomes the energy of the radiation. And then here in the end, the chi and the neutrino are all at the same temperature. Somewhere here, I think chi decouples, I don't know where, but because even if they decouple, they still have the same temperature. They're just separately evolving, right?
So there is not an experimental constraint on that, like somehow in the standard model you have, like you said, this famous factor, and so it's telling you, given the photon temperature, which we measure, that this is modifying it's telling you what the expansion rate is, right? And so I could imagine, I just don't remember my cosmology, it's been a long time, but do we have a measurement of that number essentially, that 411 factor? Because it is telling you the contribution of neutrinos to the expansion of the universe.
Yes.
Right?
Yeah.
And roughly from sort of recombination until now, it seems like something we know about. So
Yes.
can you really live with that curve being below the dashed line? That's
Yes.
my question.
That's a really good point. Actually, this is also the trick we're playing. And even though neutrino itself goes below the expected temperature, but they are compensated by the extra radiation. So the total expansion rate is still maintained the same. But
So you kind of have to tune that, right? So you have to kind of have the right amount so that...
No, we don't know the temperature exactly. We don't have direct measurement.
You don't have the temperature of neutrino
It's
directly.
inferred from any effective, I think.
Yeah. So
we know that through any effective.
so you assume all
I
the
see, it's
expansion.
absorbed, it's absorbed, you're right, yeah, it must be. It's absorbed into an effective.
Yes.
And so basically you've got one number that you have to reproduce.
Exactly. I just have to reproduce the right expansion rate, which is controlled by the n effective.
Okay.
And
It's
then
just that the standard model gives you n effective equals
3.0,
3,
whatever.
the number, it automatically gives you a number where that number agrees with experiment. Now, it's a free parameter that you
Exactly.
can fit it to
Uh-huh.
be, okay. I
Yes,
got it.
yeah,
Makes sense.
exactly. Yes, yeah. So the trick is to actually just, take advantage that the cosmology doesn't really care where the radiation, what the species is, as long
Yeah.
as there's just some radiation.
Sure.
Right, so, so that's that sort of played out nicely, and then and so in this model we end up having some sort of parameters that are important. One is the neutrino mass, which is important because it controls the coupling, because it's a type 1 seesaw type of model. And there is the scalar mass, and there is the heavy, right-handed heavy neutrino mass. This sort of goes together almost all the time. The scalar to the right-hand neutrino, scalar to the dark radiation, and this is the sort of the scale you have to have in order to get everything right. Okay, so the right-hand neutrino is way heavier than the MEV scale. M5 is usually like 100 keV, something like that. 110 keV, I think. 100 K, yeah, here it's 10 keV. M-chi is assumed to be similar mass of neutrino because there are planar rows of neutrinos, so we're just letting them to be similar. So we did the scan for this model. So this is a 2D scan. This is showing the so this vertical axis is the total neutrino mass. This is what we're scanning. The horizontal axis is the scalar mass. Oh, we're almost there. So we're scanning these two parameters, but fixing the other ones because the other ones we don't really directly measure anyway. So these two are sort of more interested. And then the color, this gradient shows the effective relativist species coming from neutrinos. Okay, so 3.04, 5 or 46, whatever is the one you expected from standard cosmology, and then it can be, by introducing extra radiation, you can cool the neutrinos down to 2.25, like here. So in this scenario, this white region are all like cooled down by this model. Here we place some other bounds. There's the Cutring bounds, just the terrestrial experiments that neutrino cannot be, mass has to be lower than 0.45. Here is the neutrino dash line is the oscillation. So neutrino mass cannot be below this if they want to do oscillation. And here there are some other curves, right? This blue contours and some SI and MI. We're going to explain that. So SI MI, this is some MCMC fit with different data sets. So I believe this DESI is the latest DESI 2024, plus the Planck 2018, some legacy data sets. So ignore the green line because this is for some other scenario. So just the red contour, here SI and the MI are the two type of interacting neutrino you get by fitting the Planck plus DESI or Planck alone. Okay, assuming the neutrinos are cooled to 2.25 for it with its contribution to N effective. So here we indicate these regions on this like parameter space. Okay, like here. What's the other one? So yeah, so this is the self-interaction part of the story, and the other part is the neutrino mass bounds. Okay, so here, this also just look at this boxed place. There's like many different curves, but what you can do is Planck plus DESI. If you do lambda CDM, the neutrino mass the mass bound is around here, 0.0788 EV. But if you allow neutrinos to be cooled to 2.25, and it's with its contribution to N effective to be 2.25, with rest of them coming to from dark radiation, the neutrino mass bound can be relaxed to be above 0.1. Okay, so this is the other side of the story. And then one can just like, by scanning. So this is for 1 point, right? The n line as one of the point, and then if you
This
change.
is assuming chi is lighter, therefore
Chi is
lighter than whatever heaviest neutrino. Right.
yes.
Basically,
It's massless. Yes, yeah. Here,
So-
I think chi is massless.
And
actually.
only one chi, right? So there's
Yes, there's only one chi here. Yeah, exactly. There's one chi here.
If you introduce more chi, then that be even better.
Yes, this is more chi. Yes. So you have like a slightly increased region. Yeah. So this is more chi. Yeah, this is 2 chi. This is 1 chi. Yeah. Great. Yeah. So that's like the story. That's it. Really. We just this is this again the 1D posterior from my collaborators. They're like experts in doing these like fitting. I can never do these myself, but they can do these things. Yeah. So conclusion. So these are the questions we had in mind, and then we think, oh well, maybe if you're introducing self-interacting dark radiation, it helps solve or explain or help these questions we had in mind. That's what I want to share today. Thank you.
But does this model believe the Hubble tension as the self-impacting neutrino one?
Yeah, no, we didn't go that far. We didn't go that far. We didn't go that far actually.
And so this you didn't really emphasize it, but this is a model where phi is coupling. I assume your notation here means on the upper right that it's coupling to the right-handed. NC is the right-handed neutrino, yes?
Yeah, N
Capital
is the
NC.
N is the right-handed.
Yeah.
NC is just the
Right, and
left-handed.
so now you can get this from just that coupling, which,
Yeah, and we didn't really explain where these come from. It's just it's sort of you just write down the way that is okay with QFT.
yeah,
Not worrying about where they come from.
Well, it already has a name. It's the Myron.
Yeah, if you make you make it like a spontaneous thing from something else, but then there's some issue. Yeah, we try to avoid doing that because then you need to have extra stuff, and that messes up with the chi mass, for example. So imagine if this is like some complex scalar, and then you do the Marion type of thing. The scalar, this chi will no longer be as like light.
Unless
Just depends on its coupling.
Yeah, unless you tune it. Yeah, unless you tune it. Yeah.
Tuning a coupling is better than tuning a mass.
She also needs some specific coupling around that chi, so it's not free. But you can cancel against some tree level
Yeah.
by tuning.
Yeah. So.
you'll get a loop level contribution to the BEV, right? I mean, just the fact that you have both a phi coupling and a Majorana mass for n, if you just look at that can't forbid a BEV, and there's just a one loop tadpole, right?
That's true. Yeah.
So, I mean, it's going to be tuned for sure.
Yeah.
So, can you go back to your almost summary slide?
This one. This is more
So
like.
you have the nice middle strength all the way at the end, right?
Yeah, but towards the end, actually, it's like sort of closing up. So here, if you go down to like this end, it's like no longer cooled. It's sort of not as cooled, I think, this end. But this end is like constraints from BBN. So this we actually compute what is the total N effective. So this corner is ruled out if the total N effective is bigger than
Sure, but
3.4.
in the middle, it's fine.
Yeah, no, here is fine. Yeah, here is fine. There are some, but the SI place has like a more relaxed, let's say, neutrino mass balance. So somehow it's.
The MI is closer to being discovered.
No, but it's not. It's not. It cannot. Why? It cannot be discovered, right? It's just. It's as good. I'd say it's as good as lambda CDM. It's not.
I mean,
as
if you increase M5, if you kept going to the right, eventually this equilibration business is happening during BBN, right? And that's why you're eventually getting into this region where BBN is excluding you,
Yeah,
right? If you
exactly.
move further to the.
Yeah. If you go too high, it's messing up with the BBN, and then it's not as good. Yeah.
It's discovered in the sense that it's excluded.
Yeah.
So between the SI and I, it's ruled out by ACT and the count. Is that?
No, it's not ruled out. It's just not as preferred. It's not ruled out. It's this exclusion is going up, so anything below is good. So going up is bad.
Yeah, you need to get between the blue and the dash, right? That's the region.
Yes.
But you prefer the pink region.
Yes.
But the non-pink region is not preferred by ACT, something, right?
Yeah. So one of the pink regions not preferred by ACT. Yes. Well, actually, I have no control of which data sets they want to use for their fitting because I don't know anything about these fitting. It's kind of so they always have Planck because it has like a very good precision, but the L is low compared to the ground-based telescope. So they combine like part of the other data set that has high L's, but not as good as Planck data, something like that. Yeah.
So I mean, if you could make eventually a plot where you sort of put in everything, right? You try to fit everything, and then you're sort of saying that you think you will end up with maybe a blob in the SI region and another blob in the MI region, something like that. If you
we're still thinking about what is the best way to do this. Because we don't want it to be like too busy. Right now it's like this. We haven't thought about.
Yeah, it's not.
No.
In principle, you could put some kind of just combined likelihood, right? I mean, you just.
Yeah.
What about the statement Daisy saying the dark energy is not constant? Does it have anything to do with
No.
It's a complete separate story?
Yeah, it's like very different. I think the Daisy one, like the dark energy story, is a very late universe type of story. So I don't really know. I haven't studied that part.
All right.